So in this video, before we start doing some derivations of linear regression lines, we're going to have to define error and deviations. So we're simply going to look at n data points such that we have n data points. So x1, x2, y1, y2, and so forth, all the way to xn, yn. We have n data points, and we're going to assume that we only have this set of data points. We're not adding sets during these calculations, so this is a constant value of data points, and that'll be important to note in later derivations. So we're going to plot these points in the xy plane, because simply we have a two-dimensional set of data points. One dimension here in the x direction, and another dimension here in the y direction. So we're going to plot these points on an arbitrary xy plane. So this could be like an experiment you're doing, and you took the data points, and this is what you got. They're arbitrarily scattered across this plane, and we're gonna, a usual thing that people might think of when looking at data is finding the middle point of the data points. Since this is a two-dimensional set of data points, we're gonna look at two average values, such that the average lies in between the data points in each direction. So simply the average data point for the x values can be defined as x bar, which would lie somewhere around here. So if you take all the x values of each point, added them up, and divided by the total number of data points, we will get some value x bar, and we're going to simply draw a line that indicates the average value for that dimension. And then we're going to do the same thing for y bar. So we add up all the points in the y direction and divide by the total points n, and we'll get some y value such that we get that. And this intersection later becomes an important thing that we use in linear regression. So this point right here, that intersection can be relatively significant. So this is a typical thing that people would want to find out, the average point in each direction. So this becomes an average point, such that this becomes x bar, y bar. So that's basically the middle point of all your data points. And, a typical thing, what would be the deviation from this point, let's call this xi, yi, an arbitrary point that you have, like what is the deviation, or how far from it is it from the x bar line or the y bar line? So I'm going to denote these deviations, or these distances, as d subscript y and d subscript x. So that's a deviation in the x direction with respect to x bar, and this is the deviation in the y direction with respect to y bar. And y bar or x bar is just another notation for the average point. So now we could define deviation by the difference of this point to these lines. So it's simply the difference between an arbitrary point in one direction minus its average value in that direction. So we could write deviation of y in the same fashion as x, the deviation in x. So a typical thing is just to find the total deviation. Let's say, since we have n data points, we want to add up all the deviations of each data point to these average values. So we could rewrite, we want to find that total deviation by taking the sum of all deviations with respect to each dimension. So we want to find the sum of all deviations, xi minus x bar, and that simply becomes your formula for that. Now, something I want to note is that this notation, sigma, is simply the same notation as I equals 1 to n, because we have n data points and I is just the iterator, so you add each new x value for each iteration. So I just use this for simplification when doing algebra or basic mathematics, because it's a lot more easy to write this than that. So now I'm going to show you that there's a problem with this formula. There's a problem such that if you do this summation, it would always equal 0, which is kind of astonishing, but we'll prove that in a bit. And the reason why we need to prove that is because this equation starts to become meaningless. Because if we want to find the total error in something, this equation will have you subtract some error from the positive errors, such that if you do an error from this point with respect to x bar, this point is greater than x bar. So if you have xi greater than x bar, we'll have a positive deviation. However, if you choose a point in this portion of the graph, this value is less than x bar. So we have a smaller value than x bar. When taking this subtraction, or this difference, that will cause it to have a negative value. And when you add up the positive and negative deviations, what happens is that some of the errors cancel out. In this case, all the errors cancel out such that it would equal 0. So when we try to optimize equations such as linear regression lines, it doesn't become helpful when we always have a deviation that equals 0. So we want to add up the total deviations, which we'll see later. So right now I'm going to prove that this is always equal to 0. So we're going to do this. So we're going to rewrite this. So dx equals the sum of xi minus x bar. And what I'm going to do is distribute the sigma to each term. So this becomes xi minus the sum of x bar. So before we move on, I have to point out something. This x bar is constant because we have n data points. That doesn't change. So the average value does not change. So we can actually pull x bar away from the sigma notation, or outside of the sigma notation, and treat it as just a constant. And what that becomes is that it's just an iteration of x bar n times. And I'll show you that right now. So we could write it as x bar times the sum of I equals 1 to n of 1. And simply this becomes 1 plus 1 plus 1 plus 1 plus 1 all the way up to n times. And basically that equals just n times, or 1 plus 1 plus 1 equals 1 times n, the number of data points. So we could further rewrite this equation as xi minus n times x bar. So earlier we defined x bar as the average value of the data points. So we could rewrite x bar in terms of sigma notation. So we could say x bar is the sum of all data points from 1 to n divided by the number of data points, which is n. So we're going to use this simple fact and plug this into the equation. So the sum of xi minus the sum of xi times n, or over n, times n, because that n value is still there. And we could simplify this, and you'll see that this equals 0 all the time. So we get the sum of xi minus the sum of xi, which equals 0. So what this is saying is that if you take any arbitrary data points and you calculate the average values of those data points, and you calculate and you add up all the deviations from the average value, you will always get 0. So this becomes a problem because we later want to optimize the deviations or the error, because we want to find a line maybe that best fits the data points. And if the sum always adds up to a trivial solution or a trivial value such as 0, we can't really do anything with that. And we know it's not really 0 is because we know that deviations do exist, such as in this picture that I drew. And it's masked by the sum of the deviations being negative and some of the deviations being positive. And with that problem, we get a bigger problem such that you take the sum of the deviations, we get 0. So you know, and a pretty instinctive thing to do is actually take the absolute value of these deviations and add those up, which can work, but again, that's not easy to work with. So we can actually define the deviation in that notation, which is good and all, but it's not easy to work with because we have this absolute value. Later on, we're going to try to optimize this deviation or the sum of the deviations, such that we get a line that has a minimal error that fits the data points. So what that obviously requires is calculus, and when we take the derivative of an absolute value, it's not really easy to do because it's not a differentiable function. So what we can do is actually take the square of the difference, and that allows us to do the power rule instead of, you know, splitting up this equation into a piecewise function and then taking a derivative with respect to those two different functions. So now we're going to rewrite the deviations in x, or the sum of the deviations, as this. So we're going to take the xi minus x bar, and we're going to square it. As you can see, if you square the value, when you take the difference of one certain value with respect to the average value, we'll get either a positive or negative number. But that doesn't matter because we're going to square that value, and we're going to get this as the error. So we could simply note that xi minus x bar is greater than or equal to 0, and that the sum of xi minus x bar squared, I realize this is squared, is greater than to 0 for more than one data point. So this is what I wanted to lead up to, because we're going to use this idea of the difference of squares to optimize future linear regression lines. And this becomes a very typical thing, and this comes out in the derivations as well. So I'm going to define all the sum of squares. This is called the sum of squares with respect to x, but we're going to redefine these values or these summations as follows. So we can rewrite xi minus x bar all squared, and we could redefine the notation, and typically written like this: capital S x x. So you can think of it x times x is kind of like x squared kind of thing, and you'll see why this notation is important for a future thing that I'm going to write. So there's also 1 in the y direction. So the sum of yi minus y bar squared. And then there's a final one, which is sxy, which is the sum of xi minus x bar times yi minus y bar. And this one comes from some mathematical derivation, which we're going to go through in a future video. But these are the main ideas that I want to point out to you, because later on we're going to use this to optimize linear regression lines. So this is a thing to point out and, you know, keep in mind when coming with the future videos that are going to come up.